Hi everyone. So let me start today's lecture by just a small reminder about what elasticity is, what we did last time, and what we learned about elasticity, and then we'll talk about an example. Not the most simple example, but kind of typical example. So first, the mathematical definition of elasticity is just this. Elasticity as a function of price is this function. Price divided by quantity multiplied by derivative of quantity with respect to price. And last time you've seen interpretation of this, what this quantity actually means. And it meant the percentage change in quantity divided by percentage change in price. And percentage change means just relative change. It means like relative to the price level, how much the price changes is the percentage change in price. And similarly for the quantity. And the interpretation we gave to this was if price changes by X%, quantity changes by S times epsilon%. So that's more or less what we know about elasticity. We know how to find it, what is its mathematical formula, and we know also what it means. And also introduce some names for various kinds of elasticity. When it's greater than 1, when it's smaller than 1, we know that elasticity is negative, so we talk about absolute value. And we have these cases. This one is called elastic demand. The quantity changes a lot when you change the price. Here it is inelastic demand. And here it is unit elastic. And each one of these cases had implications about revenue. In this case, as price goes up, the revenue, well, what happens to the revenue? Yes, let's think. So, if elasticity is greater than 1, small change in price leads to a large change in quantity. Large negative, well, small increase in price leads to large decrease in quantity. So the product actually decreases. Here, as price goes up, the revenue increases with the same argument. So as price goes up, the quantity changes, a bit smaller but not by much. And finally here, revenue is maximum. Okay, so in short, this summarizes what we did last time. So now let's solve a somewhat typical problem about elasticity. So, problem. Suppose you are given the demand equation in the following somewhat strange way. 10,000 p squared plus 100 pq plus q squared is 70,000. First question, find elasticity when price is equal to 1 and quantity is equal to 200. Second question, find price and quantity that maximize the revenue. Okay, so you are given a demand equation, but it's not the typical way that you are given a demand equation. We are somewhat used to getting a demand equation in the form P is a function of Q, or rather Q is a function of P. So this demand equation, well, describes some dependence between price and quantity. And if you try to draw this dependency, you'll see that actually it is, well, quite typical one. As price goes up, quantity goes down. So it does define some dependence. And you can, in fact, write Q as a function of P in this case. Because, I mean, yes, you can. But it's not a simple function. Don't being a simple function, it is somewhat complicated to actually write down P in terms of Q. But still, we want to find the elasticity. So any ideas how to go about it? So first thing to notice is to find elasticity, well, you know what is P and Q in this problem. We'll be talking about this price and this quantity. What you do not know is the derivative. What is dq by dt? So how to find derivative?
Implicitly differentiate and then solve for
differentiation. Exactly, yes. So we are given dependence, but we are not given function. But that's okay, let's just differentiate implicitly. So apply to differentiate implicitly with respect to what? Well, naturally I want to differentiate with respect to price, because I want to find the derivative of quantity with respect to price. So apply d by dp. So now it's not enough just to say differentiate both sides. We have to say what is our variable and what is our function. And here when we say apply d by dp, it's clear that what we mean is p is our variable and q is a function of p. Okay, so let's actually apply d by dp. So derivative of 10,000 p squared is 20,000 p. Because derivative of p squared is just 2p. Then we have a product, 100 p times q. Let's apply the product. So 100 goes just as it is. Derivative of p is 1. Derivative of, q is just q. And then we leave the first factor, p, and differentiate the second one, dq by dp. Okay, and finally, we have to differentiate q squared. Well, q squared is a function of, q is a function of price, so derivative of q squared is 2q times derivative of q. So it's 2q times dq by dp. And on the right side we have, of course, 0. Derivative of 70,000 is 0. Okay. Now we do have a dependence between p, q, and derivative of dq by dp. Let's now just isolate what is dq by dp. I'll move everything with it to one side, 100p plus 2q. Everything without it, I'll move to the other side, minus 20,000 p minus 100 plus 100q. And I put the minus sign in front of everything. So dq by dp is minus, let me factor out 100, 200p plus q over 100p plus 2q. So we completed the first step, finding the derivative of q with respect to p. Now we have an expression. And now it's really easy to find what is the elasticity. Elasticity we know is just p over q times derivative of q. We know the derivative of q, let's just multiply by p over q. So we have this expression for elasticity, minus 100 p over q times 200 q over 400 q plus 200. So we found the expression for elasticity. It's of course important. And to answer the actual question, all we have to do is just plug in the numbers. We know what is p, we know what is q. We should just plug everything in. Elasticity and the point where p is equal to 1 and p is equal to 100, 200 is minus 100 times 1 over 200 times 200 times 1 plus 200 over 100 times 1 plus 2 times 200. So we get minus 1/2 times 4 over 5. So it's minus 2 over 1/2. Okay, so we found the elasticity. Maybe before we go to the next part, let's interpret this number a little bit. So the demand here is clearly inelastic. Change in price leads to only a small change in quantity. More precisely, if P changes by X%, U changes, let me say, if P increases by X%, U decreases by 2 over 5x%. For instance, if P increases by 1%, U decreases by 2/5 or 0.4%. In this case, so if the price increases by 1%, the quantity will decrease by just 0.4%. What will happen to the revenue? Well, revenue is price times quantity. If you increase the price by 1% and decrease the quantity by 0.4%, it means that the product will increase by 0.6%. So it gives you, well, a pretty good understanding of what happens if you change the price just slightly. Yes, maybe I forgot to tell it. Here what I mean is for x which is small. So all these considerations are just, well, approximations. They become better and better as x becomes smaller and smaller. And here, say the product doesn't actually increase by 0.6%, but it increases by, well, the product of 1.01 and 0.9996. but it is pretty close to 0.6%. So this works approximately, but the approximation becomes better and better when x becomes smaller and smaller. Okay, so maybe questions about this first part. Yeah. So what happens is, it's general. If you have two quantities, if one of them increases by A% and the other one decreases by B%, the product will increase by A minus B%. Well, if both A and B are small. What I mean is, you have this formula. A 1 plus A times 1 minus B is 1 plus A minus B minus AB. So if A and B are small numbers, this is 1 plus the difference of A and B, and plus a small term which is really, really small. So 1 plus 0.01 times 1 minus 0.04 is, so 0.04 is 1 plus 0.006 and minus something really, really small, 0.0004. So the main part, the main change is this 0.6%. So it's quite general. You increase one of the quantity by 8%, the other one decreases by B. The product increases by A minus B, provided that A and B are small. Other questions? Okay, so what this part teaches us is, well, sometimes demand equation is not given to you explicitly, it's only given to you implicitly, but that's no problem for us. We do know how to differentiate even implicitly. Okay, let's go to part B. Part number 2. So we want to find the level of price and production level which will maximize the revenue. So how can we do this? Yeah. Exactly. So since we already computed the elasticity, the most natural thing would be just use it. We have an expression for elasticity, and we know that revenue is maximal when elasticity is minus 1. One elasticity which is negative 1. i.e., I want this quantity to be equal to 1. I mean, the one without minus sign to be equal to 1. So 100 P over Q, 200 P plus Q over 100 P plus 2Q. I want this whole thing to be 1. So about this minus sign will be minus 1, this thing should be 1. Okay, so I want this quotient to be 1. Let's simplify it. Let's say the numerator should be equal to denominator. So 100p times 200p plus q is q times 100p plus 2q. Let's open the brackets. 20,000 squared plus 100q is 100q plus 2q squared. So fortunately for us, we see some simplification. This 100q gets cancelled out on the two sides, and I can divide both sides by 2. So I get 10,000 squared is 3 squared. And I can extract square roots. So 100p is q. By the way, why is it 100p and not minus 100p? Why did I take the positive solution and not the negative? Why did I ignore the negative? Yes, it's actual problem in economics, business. We don't want negative prices, we don't want negative quantities. So P is not negative and Q is not negative. So we take only the positive sides. Okay, that's very good. We found that Q must be equal to 100p. But that's not enough. We actually wanted not a dependence of P and Q, we wanted actual price and actual quantity. But we also didn't use everything that we could use. What else can we use? This one, exactly. We can still use the demand equation. We know that for every price and quantity which are relevant to our problem, the demand equation must hold. In particular, for those which maximize the revenue, it still must hold. So now, let's take this dependence, use 100p, and plug it into the demand equation. What will we get? We'll get 10,000 p squared plus 100p times q, which is 100p, plus q, which is 100p squared, is 70,000. So if you open the brackets and add everything up, you'll get 30,000 p squared is 70,000. So p is equal to the square root of 7 over 3. And q is 100 times p. So 100 times 7, square root of 7 over 3. Okay, that's the answer. So, well, basically we have just confirmed the conclusion that we made here. That if you, from this, to maximize the revenue, from this price level you should increase the price. And in fact you should increase it all the way up to square root of 7 by 3. Questions about this part, maximizing revenue? Okay, so I have several comments. First comment is that such problem is kind of very, very, very typical of the problems that you're going to get on, say, the coming midterm. It's, I mean, you will get a problem with this kind of questions. Maybe find elasticity, given a demand equation which is given to you, so implicit function, maybe some function with powers, so you might have to apply logarithms, interpret the elasticity, find the level of price and quantity which maximize revenue. So all these things are very, very typical questions about elasticity. Another comment is, well, sometimes we want to maximize revenue, but we are not given a question that tells you, well, find the elasticity. In this case, you can proceed in two ways. One is, well, even though people don't tell you find the elasticity, do find it and equate it to -1. That would work. Another option, just find the marginal revenue and equate it to 0. So that would also work. Find the revenue, find its derivative, and equate it to 0. This way you will also find the maximum of revenue. Okay, so any questions about elasticity in general?
What are you doing over there? Left, right?
This one? I was just explaining this result about what happens to revenue. As you increase the price by 1% and decrease the quantity by 0.4%, what happens to the product? And I told, well, that's exactly what happens. P times Q gets replaced by P times Q times this times that. And this is approximately 1 plus 0.006.
But not exactly?
Not exactly, no. So you still have this correction, but this correction is of order of 0.04%.
So when we say our answer, you just say 0.6%.
Yes, so the meaning of this phrase is not an exact phrase. It's like for marginals. I mean, when we talk about marginal, I don't know, profit, we say that as you increase the production by 1 unit, the profit will grow by the marginal profit. That's, well, that's kind of white lie. Yes, it will grow approximately by this amount, but not exactly by this amount. But it's okay. If you want just to analyze what happens, I mean, how change in price will influences the policy of your business, well, you don't really care about the exact numbers. You just want to know whether it increases, decreases, and, well, how fast does it increase. So that's exactly what we are doing here. That's why I'm saying that for small increase in price. Yeah?
I wonder why revenue is maximal when it is really elastic.
Yes, so that's exactly the statements that we had before. You know that if elasticity is greater than 1, so if this happens as price increases, you know that the revenue will decrease, right? So if elasticity is greater than 1, you can make the revenue greater by decreasing the price. You can also make the revenue greater if elasticity is smaller than 1. Because you should just increase the price. So if elasticity is either greater than 1 or smaller than 1, you can make a change to increase the revenue. But at the maximal point, you cannot make such a change. It means that the only option is that elasticity is -1. So R is maximal when epsilon is equal to 1.
So R is maximal when it can change.
Because there is no way to change the price to make it even bigger. Okay. Other questions? Yeah. So once again, it's this computation. The price gets replaced by 1 plus 0.01 times price. The quantity gets replaced by 1 minus 0.004 times quantity. And then the product gets replaced by the product times this amount. And this amount is, well, just look at this formula. It becomes 1 plus 1% minus 0.4%, which is 0.6% altogether, and plus a small correction, which is 1% of 0.4%, which is very, very small. So we ignore this small part. So basically, the general thing to remember is for small numbers A and B, if you multiply, I mean, if you increase one quantity by A% and you increase the other one by B%, the product will get increased by A plus B. Other questions? Okay, so let's go to another different topic. Actually, I would say simpler than this one. It's a topic of compound interest. So first, what is it about? It's basically about what happens when you have an account, say a bank account, and in this bank account you earn 2% interest every year. Well, what happens then? Well, you wait for a year, you get your 2% of the sum that you have in your account, and you decide to put it back into the account. It means you reinvest the interest. And all we are going to do is just analyze what happens if you repeat this procedure over and over for several years. Okay, so let's indeed analyze what happens. Suppose you have $P in an account that earns interest of 2% per annum. This just means every year. So suppose you have $P in an account that earns such an interest, and you reinvest the interest every year. First, almost kind of obvious question is, in 1 year, how much money will you have on your account? And this question is really obvious. You start with $P inside of your account, you wait for a year, in 1 year you get, well, 2% of these $P. So you add to these $P another 2% of P. So you can say that you take P and multiply it by 1.02. Well, what will happen in 2 years? Once again, it's really easy. It's just, well, it's what happened in 1 year, and then you wait for another year. It means that you start the first year with this amount of money, P times 1.02, and now you wait for another year. So you'll get another 2% now on this quantity. So it means that this quantity will now get multiplied by 1.02. So the amount of money in the end will be P times 102 squared. Well, the obvious generalization in X years, you have every year your quantity, the amount of money in your account, will grow by 2%. So every year it will get multiplied by 1.02. And this will repeat itself for X years. So the final answer would be P times 1.02 to the power X. Okay, so this is really just common sense, nothing interesting happening here. We just will do some simple arithmetic. Let's try to think about what kind of growth do we have in this? What kind of growth do we have in this account?
Exponential?
Exponential, yes. It's a constant times something raised to power x. If if we try to graph what happens. Well, it will be almost our usual exponential graph with small change. We are only allowed to consider what happens at integer times. We are only allowed to take our money in the end of the year. So we have such a graph. P times 0.2. And you will get such points at time 1, 2, 3, 4, 5, 6, and so on. It is almost the graph of an exponential function. Except we are not interested in the whole function, only at some points in this graph. And this, to be honest, is quite inconvenient. I mean, it is exactly what happens in real life. In real life, we do put money into an account and we get, interest compounded either annually or semi-annually, but that's more or less it. Maybe, well, monthly. Some accounts offer monthly interest for you. But it's really inconvenient for us to talk about what happens at discrete, at separated points of time. Instead, we would like to talk about real functions, something like an exponential function. So, the way we solve this problem of not having kind of the graph in between integer points is, well, we know that even in real life we have accounts which offer, say, monthly interest payments. We wait not just for the whole year, but for 1 month. It means that on this graph you will have, in each such interval of x1, extra 12 points. Well, that's good, but still we have small gaps. And still it's not mathematically convenient to talk about, well, these small gaps. So what we do, we imagine that, well, maybe there is an account with weekly compounding, weekly interest payments. Well, still, it's better, but still not really a function. What about daily interest payments, hourly interest payments? So we take this interval and decrease it more and more and more. In the limit, we'll actually get kind of continuous compounding. It means that at any point in time, you can go to your bank and take the interest. And if you go just 1 second later, you'll get just slightly more interest. That's about continuous compounding. But now we want to analyze how to describe mathematically this continuous compounding. Well, one obvious thing is whatever the interval here is, it is still, the growth still will be exponential. It will be the principal times 1 plus the interest for this period, say 1 month or 1 second, times, well, to the power of number of periods. So whatever it is, it will be an exponential model of growth. So let's talk about continuous compounding. Well, the amount of money at time x, amount of money after x years, we'll take it to be, well, it should be the principal times some number raised to power x. So we just say, well, we'll consider such a curve, and we'll just say that this curve tells you what happens at any moment of time x. And now x is not necessarily integer. Okay, so we get some kind of formula, but we have this, when x is equal to 0, a of x is equal to p, so p is obviously amount of money times 0. We also call it the principal. But this b, well, it should reflect something about the rate. It should be different for different rates. But how is it related to rate? Well, let's think for a second. What is the rate? What does it mean that I have, say, an account is 2% rate per year? It means that the 2% tells you it's about not the rate of change of the amount of money, it's about the relative rate of change. So 2% is the relative rate of change of the amount of money in your account. So let's write it that the rate, interest rate, let me call it R, is, well, it's the relative rate of change in the amount of money in the account. That's exactly the figure that people quote when they say interest of, say, 2% per year. It means that the relative rate of change of the amount of money in your account is 2% per year. But now let's compute it. Given such a formula, what is a prime over a?
Ln AX.
Yes, exactly. So it's not really convenient to differentiate such a thing. But we also know that this thing is the derivative of 1 of a of x, 1 of a of x, just from the chain rule, or from logarithmic differentiation. But 1 of a of x is really simple quantity. It's 1 of the principal plus x times 1 of b. And what is this derivative? Well, the principal is just a number. It's how much money you have now. 1 of b is once again a number. So it's kind of 5 plus 10x. What is the derivative? Of course 10. In this case it is just 1 of b. IB. Well, this b is actually e to the power r. So this base, the number which we are raising to power x, is exactly e to the power of a. So now let's have, well, the final version of this formula. We'll put it in a big box and remember it well. So continuous compounding is described by the following formula. The amount of money is the principal times e to the power r x, where a is the amount of money, which is the same as a at the point 0, which is the principal, r is the interest rate. Which is compounded continuously. So let me repeat the logic of this small derivation. Yeah.
Sorry, I didn't get how you transform the ln p plus x ln b. You take the derivative and it becomes ln p.
So from here to here, or from here to
From
here?
the second.
From the second to here.
No, that one too.
So here it is
Yeah,
derivative of this thing is 0.
Yeah.
Derivative of x times 1b is, well, 1b is also a number.
Oh, okay, yeah.
Yeah. So let me repeat a little bit about the logic of what we just did. We said that, well, in a not continuous compounding, when you get the interest in the end of some terms, say year or month or week, we have, well, an exponential model of growth. And the only problem is that in this formula we can't take the x in this formula to be non-integer. Well, then we told, actually, regardless of what the period, what the term is, we always get an exponential model of growth. So let's take the term to be almost 0, but still we'll have some exponential model of growth. The only problem is that in this exponential growth, we don't exactly know, well, how is the rate related to this base. But actually we do know, because the interest rate is just the relative rate of change of this amount. So in fact, we can find the relation, and well, it leads us to this formula. Let's try a very simple example. So if you invest $10,000 at 3% compounded continuously. How much money will you have in 1 year? Okay, so how much money? Well, very simple question. We just know what is the principal, how much money we have right now, 10,000. We know the interest rate, and we should plug into this formula. So amount at the point 1 is principal 10,000 times e to the power of rate times x. Now, small point, the rate is quoted here as 3%. It doesn't mean that R here is 3. It means that R is 0.03. We express this 3% as an actual number. So 0.03 times 1. So here P so this is approximately, if you take a calculator and try to find what it is $10,300 and $4.50. Just a small comment, the rate is 3%. As a number, it's 3/100 or 0.03. And we always use the rate as a number, not as percent. Okay, so let's think about whether this result is reasonable. If you put your $10,000 in an account which earns 3% not continuously, but just, well, in the end of the period of 1 year, you get 3%. In the end of this 1 year, you would have $10,300. You would get exactly 3% of these $10,000. But here you get slightly more. You get an extra $4.50. Where do they come from? Well, let's think about it this way. If I get my interest only in the very end of the year, yes, I will get just $300. But if I say collect my interest in 2 steps, in half a year I come and I collect half of my interest, $150, and put it into the account. Well, then I wait for another half year, but now I get interest not only on the $10,000 which I had, but also on this additional $150. Well, it's not really that much of interest, it's just $150 times another 1.5%. So it's basically something small, a couple of dollars, but I do get some interest on interest. And here in continuous compounding, I don't go to the bank every half a year. I go to the bank, well, every day I come, collect my interest and put it into the account. In fact, even more frequently. I do it kind of every second, every moment. So that's where these extra $4.5 come from all this work of going to the bank and taking the interest and reinvesting it immediately. That's what it means to compound continuously. And you see that at least for small interest rates, the difference between continuous compounding and usual compounding, well, is not that much. So it's, first of all, it's a very convenient thing for us to talk about this continuous compounding, because now we can talk about what happens in 1.7 years. Just as easy. Instead of 1 to 1.7. But also it's also very good approximation to the reality. Okay. How about 20 years? How much money you will have in 20 years? Well, also not very hard. 10,000 times e to the power 0.03 times 20 happens to be about $18,221.19. So a little bit less than double the amount. Okay, so that's how we solve these most straightforward questions. Another kind of straightforward question is, so maybe first question about this. It's really simple, but still maybe it is confusing. So any questions?
How do you do it biannually?
Say again?
How do you do it biannually? Like every 6 months, how would you do that?
Oh, I would take 10,000 and multiply it by, so every half year you get 1.5%, so you multiply by 1.015, and I wait for two half years, so square. So I would take 10,000 multiplied by 1.015 square. This is 1.5% for half a year. So 3% per year is 1.5% for half a year. But well, I mean, we mostly will not be discussing non-continuous interest. So mostly we'll be discussing just continuous interest. Okay, other questions? Okay, so yeah. So another kind of question is, if you want to have $100,000 in 20 years, you count the terms 3% per annum compounded continuously. How much should you invest? So now we are talking about kind of planning problem. We have a given target, we want to have $100,000 in 20 years. We know what kind of account we are using, and the only question is how much should we put into the account right now. Well, also very simple problem. You know how much money you will have in the end, so you know A of 20. So you know that A of 20 is 100,000. On the other hand, you know that it's the principal, which you do not know, times e to the power of 0.03 times 20 must be equal to 100,000. So to find the principal, how much I should put into the account now, we'll just take 100,000 and divide it by this number. Dividing by e to some power is the same as multiplying by e to the power of minus this number. And we find that it's about $54,881.16. When talking about dollars, it makes sense to round to two figures. It's just round in cents and disregard all the rest. So basically, it's without a calculator. You can't. You do take the calculator. Fine. On an exam, you just leave it as 100,000 times minus 0.6. So this question is, well, it is really simple. It's as simple as the first one, but there is some idea hidden here. Look at this formula. The amount of money that you have in 20 years times e to the power of minus interest rate times 20 happens to be the amount of money right now. It looks exactly like this formula, except we are moving not forward 20 years, but rather backwards. We take x to be not plus 20, but rather minus 20. So this formula shows that you can kind of go from the value of money in the future, $100,000, but in 20 years, back to the value right now, which is this answer, by using the same formula, but with negative amount of years. So it works, well, both with positive, with going forward into the future, and with going backwards, from the future back to now. Okay, we'll talk a little bit about this idea later, but for now let's look at third kind of straightforward questions about this formula. Third question would be, if you want to have start to invest $10,000 to get $100,000 in 20 years. continuously. New era. So it's another kind of playing problem. We know what is our target, we know how much money we have now, and the only question is what to do in between, how to go from now to the future, what kind of return do we want. And once again, it's really simple. You know the amount of money now, the principal, 10,000. You know how much you are going to wait. So you multiply it by e to the power of the rate, which you still don't know, so leave it as just r times 20 must be equal to 100,000. And all we have to do is just solve for r. So basically, let's simplify it a little bit to have e to the power r times 20 is 10. And how do we solve for r?
Log both sides.
Take over, yes. So r times 20 is 1 over 10. So r is 1 of 10 divided by 20, which once again you can take the calculator and find that it's 0.115, or you can say that it's 11.5%. So it's, well, pretty large figure, 11.5% every year. And, well, that's what you have to earn in order to convert $10,000 now to $100,000 in 20 years. Okay, now, well, first any questions. Let me ask you a very simple question, but really about understanding this. How much money will you have in 40 years if you invest $10,000 at 11.5% per annum, once again compounded continuously. So I'm taking this answer from the previous problem. I'm talking about the same problem as before, compounded interest at the rate of 11.5% per annum. And now I want to wait not for 20 years, but rather for 40 years. What amount of money will I have in 40 years? So in 20 years I have, instead of $10,000, $100,000. What will happen in 40 years? It's something you really don't need the calculator for. Say again? $1 million, exactly. So answer 1 million. Why is it 1 million? Well, we have here the growth which is exponential. It means that, well, in this account, if you put $1 into this account and wait for 20 years, it will become $10. And it doesn't matter what 20 years you are talking about. These 20 years from now to in 20 years, or the other 20 years from 20 years from now to 40 years from now. So basically, in 20 years, this amount will get multiplied by 10. In another 20 years, it will get multiplied by 10 once again. That's what it means to have exponential growth. What is constant is by how much you multiply each time. Not how much you get, but rather how much you multiply each time. Let's start to read the quiz a little bit earlier and then we'll finish also a little bit earlier.
Evan, ready? So let me read the questions aloud. First question. Find the derivative if the function is x to the power x, and just a small comment, the derivative should be expressed as a function of x. Second question. Find the second derivative, d squared y by dx squared, at the point 1, 2, if you are given the following equation. E to the power 2y minus 4 plus x is equal to y. So this is y, this is 4, and this is y.